Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the University of Helsinki in the Helsinki Institute of Physics over in Finland. And yeah, I'm a theoretical physicist and I specialize in cosmology. So that means that I study the universe, the contents of the universe, how things evolve, how things interact, all of the cool stuff happening inside the universe. Of course, I don't study all of the things in the universe, I study a subset of them. I love being a physicist. I love studying the small subset of the universe that I get to study. And I love chatting to everybody about all of the cool things I get to study in my work, all of the cool things that I get to research. So welcome. If you're a first-time viewer, welcome back. If you're a regular, it's great to see everybody here. I forgot to close my emails and now I'm getting notifications that we just closed that. Okay, you'd think by now, 8 years into streaming, I'd have my setup nailed down, and yet there are always details and tweaks and things I forget to do. Today I forgot to sign out of my emails and suddenly there's stuff popping up on the screen, but taking care of that now. At least you all don't see the pop-ups and stuff. So hello to all of the regulars. I see a bunch of you popping in here. Scott can't join today. Well, whenever you watch the replay, great to have you in the replay. First, Paul, Ben, great to see you all here. Today, we are hopefully also going out to Twitch. I am still not sure how the Twitch thing is going to work. So if anyone is seeing this on Twitch, please do just write a message. Let me know. Let me know if this is working on Twitch, if any of you are watching on Twitch. As some of you might know, Cup of Cosmology has been going on for 8 years now in different iterations, different versions. I started out on Periscope, then I moved to Haps. In the Periscope days, my streams went out to Twitter, then I moved to Haps, still going out to Twitter and to Haps. At some point, I added YouTube into the mix, so it was Twitter, Haps, and YouTube. I tried Twitch for a few weeks, it didn't really work out for me. Then Haps closed and I moved entirely to YouTube via Restream, still going out to YouTube and Twitter. And now, for the first time ever, this Cup of Cosmology, we are not going out to Twitter because I've ceased all my I've severed all connections I have to Twitter. If anyone follows me, you'll notice all my old posts, or my old likes, or my follows, they're gradually disappearing as I clean it up. So yeah, my Twitter account is officially no longer an active account. So now instead I'm trying out Twitch again. So today the stream should be on YouTube and on Twitch. Wherever you're watching from, please do all of the usual things, like the video, leave a comment, subscribe, say hello in the chat, share this link, whatever you do, it really helps boost engagement. I don't know what happened last week, but I think some of you were just really active with sharing, and last week I got like triple the amount of viewers I normally get, which just means 3 times more people to tell all of the cool things, to talk to about all of the cool things in the universe. So please do all of the usual YouTube engagement things, press the buttons, make stuff happen. I appreciate each and every one of you when you do that. So if you're a first-time viewer, testing on Twitch, thank you. I do see comments here, Paul. Thank you for testing that. I can see comments from YouTube and from Twitch. Thank you for testing that. It's good to know that it's working in both places. And I can see comments coming in from both. And technically, I can write comments on both as well, because Restream has the option where I can just write comments on both. If I start getting a lot of comments coming in from both Twitch and YouTube, what I will do is put the chat on screen so that you will all see all of the comments. As you can see now, there's a box over here with new comments will be displayed here. If I turn that on, you will get to see the comments that are coming in both from YouTube and from Twitch, wherever you're watching from. Currently, I don't think there's enough comments coming in from Twitch to make that worth doing. But if I see there's a lot of people watching on Twitch, I will do that. So you will get to see all of the questions all the time. Just makes the screen a bit busier, but we'll figure that out as we go. Twitch is still an experiment for me. We'll see if it works, how things go. If you're on YouTube, great to have you back. If you're on Twitch, welcome. If you know me already, great to have you here. If you're a first-time viewer, I hope you're going to stick around. So yeah, I'm a cosmologist. That means that I study the universe, which is a great thing to study. And the idea of these streams is that, hey, David from Michigan, great to see you. Great to have you here. I know you were in last week. Great to have you back. So the idea of these streams is that you people can ask me anything you want about cosmology, about physics, about space, about science, about academia, about my life, pretty much anything you want, and I will do my best to answer your questions. Of course, I don't always have all the answers, so we'll try to figure it out as we go. If I don't know something, I will always tell you that I don't know something. If something's not clear, I will tell you, because I don't think one of the ideas behind this show is to get rid of the idea that scientists know everything. We don't know everything. We are very specialized in some subset of field, but that doesn't mean we know everything. So if you ask me, if you ask me something I don't know the answer to, I will tell you, because I'm not going to lie to you. I'm not going to make stuff up. So you can ask me anything you want. If I have the answers, I'll try to answer. If I don't have the answers, we'll try to figure it out together. And if not, I'll write it on my list and then never look at it again and pretend I'll answer it next week and then probably forget. So that means that the direction of the stream is entirely up to you. Whatever you want to talk about, you make the stream happen. I don't have a topic prepared today, so this is literally whichever topic you want to take us in. As always, this means that I will rely on your questions. If you don't have questions, then I get to talk about some of my favorite things. So let me just start with a broad introduction here. There's already one question that I want to get to, but I want to tackle something else first, related to a question that I got asked before the stream started. Just a comment, as some of you know, I was ill over the Christmas break, and I had COVID over the Christmas break, and I'm still recovering. I'm still out of breath easily. Last week the stream was interrupted by frequent coughing fits. I think I'm a lot better now in that regard, but it might be that I still have to pause occasionally for, to catch my breath, but definitely feeling much better. And thank you to everyone who sent me messages checking in. I really appreciate all of you. So if I have to stop the stream at some point for a coughing fit, I apologize in advance, but let's see how we do, how we get on with this today. Okay, so I see there's a question about multiverse, there's a question about magnetars, which are very, very, very cool. But before we get into that, I just want to remind everybody about some stuff in the universe. So let me start by the stuff that we know. So as far as we know, the universe has three main components. Everything we see, everything we're used to, everything from the stars you see in the night sky to me, to my tea mug, to the tissue I just used. All of this is normal matter. Normal matter only accounts for 5% or 4.9% of the energy budget of the observable universe. Then there's another big chunk that is in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but doesn't interact electromagnetically. This means that dark matter, we can know that dark matter is there based on how it gravitationally affects other things, but we can't actually see it. It is invisible, which means it is very, very, very difficult to study because, of course, it is invisible. The remaining 69% of the energy budget of the observable universe is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy. So dark matter behaves like normal matter, except that it's invisible and doesn't interact with light, but we know it's there. Dark energy behaves very much like energy and is driving everything outwards. And I'm just going to hide a comment on Restream. I'm sorry, I'm not interested in buying followers or whatever it was you were just promoting. I'm not interested in that. If I wanted to buy followers, as a scientist, it's not like I have free money lying around to buy followers. I am not here to be an influencer. Anyway, I just got distracted by a big message on Twitch, but that's gone now. Okay, so the reason I wanted to mention this today is just a reminder of what these three main components do in the universe. And let's start with normal matter. Normal matter is everything we know. We're pretty sure we know what normal matter does. It's there. Then there's dark matter. Now, dark matter interacts gravitationally, and dark matter is what holds galaxies together. So dark matter is 5 times more abundant than normal matter. For every clump you have of normal matter, you're going to have 5 times that much mass in the form of dark matter. Most galaxies, or every galaxy that we know of, with some minor exceptions, has a lot more dark matter, and dark matter really holds everything together. So dark matter is heavily gravitationally bound, and it's what really is causing galaxies to come together. So there's often questions of, is dark matter contributing to the accelerated expansion of the universe, or even the expansion of the universe? And the answer is no. It is negatively contributing it to a sense, so it does play a role. So we know that the universe is currently expanding, and that this expansion is accelerating. So the universe is expanding faster today than it was in the past. This is because of dark energy. Dark energy, this 70% of the energy budget of the universe in the form of dark energy, this is what is pushing the universe outward and making it go faster. So in the very, very, very early universe, there was inflation. The universe started to grow exponentially. Let me just show an image for this. Universe started to grow exponentially in the very early universe. We had this big event where everything started stretching outwards, and then things gradually slowed down. So since then, the universe was just expanding because of this initial expansion. But the universe is full of objects, mainly dark matter, that pull it back together. So this means that what a lot of people thought is that eventually gravity would win and pull things back together. Eventually dark matter and normal matter would take over and pull everything back together. However, what we've been able to observe is that the universe is still expanding, and this expansion has accelerated, so it is getting faster. The most common thought pattern or model or proposal we have for this is dark energy, which is this weird type of energy that is pushing everything outwards. So then, in a sense, matter and dark matter contribute to the expansion of the universe by trying to slow it down, while dark energy is pulling it outwards. An obvious question to ask is, okay, if we know that the universe is expanding and this is accelerating, why are galaxies getting closer? We know that Andromeda, the closest galaxy to the Milky Way, is on a collision course with us. This is because on small scales, like 50 galaxies, 100 galaxies, the gravitational pull caused by dark matter and normal matter wins. It's only when you take a step back and look at the overall picture that you see that dark energy is actually winning. So the question of, does dark matter contribute to the expansion of the universe in any way? Yes, it would technically slow it down, but there's not enough dark matter to overcome dark energy pushing things outwards. Dark energy drives the accelerated expansion of the universe. Dark matter holds things together. Normal matter is very much underappreciated, I agree. Very, very important question here. Is dark matter and dark energy equivalent, just like regular matter and energy? Absolutely not. So we know that we can convert matter into energy. Energy equals matter times the speed of light squared. If you take energy, you can make particles. If you take particles, you smash them together, you'll get energy coming out. You can create energy. You can change energy and matter. And it's very logical to say, okay, is dark matter and dark energy the same? They're not. Dark matter is something that is dark, so it's invisible and it behaves like matter. So we call it dark matter. And dark energy is an energy that is pushing things outwards. It's not actually dark because it kind of doesn't have any color or any lack of color. It's energy. And we call it dark because it's mysterious and we don't understand it. They're very, very badly named, but there is absolutely no connection between dark matter and dark energy other than we don't understand them. So we call them dark thing. It would actually make a lot more sense to call it like negative pressure energy because it's behaving in that way of pushing things outwards, and invisible matter. But it's just not as catchy. You know, if I show the pie chart and it's like normal matter, invisible matter, mysterious energy pushing things outwards, it's not as catchy as dark matter, dark energy. But there is no connection between dark matter and dark energy other than we don't know much about them. Great. This pie chart reminds you of election polls. Yes, unfortunately, the pie chart is prettier. My pie chart is prettier. Yes. Several candidates get a lot more than they should. Absolutely. Let's not get into politics, especially with so many bad things happening in the world. Let's keep away from that topic because else I'm going to start ranting. You know, I've lived in plenty of countries and none of them are doing good things politically related. But anyway, yes. So a next important question. I am still very aware of the multiverse and magnetar question. I will come back to those. As always, I jump about a lot, but I do try to get to all of the questions before the end of the stream. So we're going to try to do that. One big important question is, where do these numbers come from? I told you we have 4.9% normal matter, 26.2% dark matter, 68.9% dark energy. Just want to make a comment. These numbers are the most up-to-date numbers. There are several versions of this pie chart going around. And some people who use this pie chart in talks and in science outreach forget to update it and will have numbers that were true 10, 15 years ago and haven't been updated. If you see a version of this chart where dark energy is at 74%, you should know that that is an outdated chart from many years ago. The numbers here are the most current numbers from the Planck satellite. If you see other numbers, we often do it as like 520, 570. That's an approximation. But if you see numbers like 75% dark energy, 74% dark energy, this is absolutely a kind of subtweet to a very specific video. If you see those numbers, just know that they are slightly out of date numbers. These here are the most up-to-date numbers. Where do these numbers come from? I'm so glad you all asked me that. You didn't, but let's pretend that you did. These numbers come from the cosmic microwave background radiation. It took all of 15 minutes today. This is the oldest light we have in the universe. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. And what you can see here is the very first light in the universe. So this has orange spots and blue spots. Let's talk about what this is and what we're seeing here, and then I'll answer the other questions. I just realized I'm talking very quickly. So let's all take a breath, have a drink, and then let's carry on. Of course, I'm talking quickly. It's the CMB. I always talk quickly, and then the CMB appears, I talk even quicker. Okay, so in the very early universe, there were three main things happening. Dark matter had already broken away, it's doing its own thing. Dark energy was not really involved in the early universe, but then we have three main things. We have protons, we have electrons, and we have photons, which are particles of light. These three are all bumping into each other constantly. Now, as the universe cools down, because it's expanding, energy is dissipating, temperature goes down. As the universe cools down, the interactions, the connections between photons, particles of light, and the other particles becomes harder. The reason is that it becomes, as the universe cools down, it is easier for protons and electrons to combine together to form atoms. So you can form the very first molecules here. So you have you have protons, and you have electrons, and these combine together. Once this happens, the photons, the particles of light, can no longer interact because the electrons are no longer free to interact. They've been coupled up. This means that the photons, the particles of light, then break away and start traveling throughout the universe, and they have been traveling since that time. They've been gradually redshifted because photons are light, they have a wavelength. As the universe expands, this wavelength gets stretched. So if you start out with a photon with this wavelength, I have a slinky toy handy just for this. If you start out with a photon with this wavelength, as the universe expands and this photon travels, its wavelength is gradually going to stretch and stretch and stretch. And by now, it's stretched enough that it is in the microwave range of the electromagnetic frequency. So this leads us to this image that we call the cosmic microwave background radiation. So cosmic, microwave, because it's in the microwave range. Background radiation, because it's a radiation we see in every direction we look in the universe. The orange and the blue spots correspond or show us where in the early universe there was more matter and where there was less. Because in regions where you had a lot more matter, the protons and the electrons could combine together faster, and then the photons had to climb out of this kind of energy well, or this place. It had to kind of fight the gravitational pull to get away. So it lost a bit more energy. So it's a bit colder today. So then you have colder photons and warmer photons. But this is a fractional difference. This is 1 part in 100,000. So it's a really, really small difference, like a fraction of a degree, warmer or colder. And by looking at how many orange spots there are and how many blue spots, how hot, how cold, we can get a snapshot of the components and basically everything happening in the universe 380,000 years after the Big Bang, or 14 billion years ago from our perspective. So where do our numbers of 4.9% dark matter, 4.9% normal matter, 26.2% dark matter, and 68.9% dark energy, where do they come from? They come from the CMB, cosmic microwave background radiation. That is a broad introduction. They are just to give you an idea of dark matter, dark energy, CMB, and also because I was asked before the stream how dark matter interacts or how dark matter is involved in the expansion of the universe, so I just wanted to address that question. It's not, it pulls things together. And now we can get into the two questions that people asked here early on, which I ignored because I wanted to go on a tangent and talk about the CMB and dark matter, because why wouldn't I? Okay, and I saw a comment from Ben saying you missed Periscope. Honestly, same. The Periscope days were, well, when I started streaming, Periscope was really fun. It's what introduced me to streaming. But also, Periscope had a lot more trolls. There were a lot more viewers. There were a lot more questions. It was really quick fire questions. I would get like 50 questions per stream, couldn't answer them all. But there were also a lot of trolls, and there was also a lot of negativity and some people with not so nice comments. So I think Periscope had a lot of really cool things, but also sometimes it was a bit too big. At least now, most of the time, the people here in YouTube on Twitch are very nice. So I don't have as many trolls as I used to in the Periscope days, and I appreciate that. But yeah, Periscope is what, I wouldn't be here if it weren't for Periscope, like not here chatting to you. Or Periscope is what started me streaming. So I think Periscope was an essential part of Cup of Cosmology journey. Okay, any progress on the multiverse theories? Question by Ben. So there's usually two different things that people think of when we talk about the multiverse. And one of them is the idea that there can be hundreds of thousands of universes out there, and that every time you make a decision, the universe splits into a universe where you make one decision and a universe where you make the other. Some of these universes will be very similar, and sometimes they're vastly different. This is a concept that is used much more in science fiction than in actual science. But then but it is something that you can think of from quantum physics, where quantum physics, which describes the interactions of particles and really small things, tells us that everything is random, right? When you measure an electron, it has equal chance of being up or down, or like spinning upwards or spinning down. It doesn't actually spin, but it's just a property that we call spin. There's a lot of randomness, when you do the Schrodinger thought experiment of putting a cat in a box with a radioactive particle that has a 50% chance of decaying. When you open the box, there's a 50% chance that the cat is alive, 50% chance that it's dead. This is random. This is something that is not predetermined. This is something from quantum physics that we know there is this element of randomness. Hey, David Dunn over on Twitch, great to see you. For anybody who is on Twitch, make sure you follow David Dunn. David has an amazing astronomy show. If you like Cup of Cosmology, you'll like David's astronomy show. That is, I believe, on Saturdays. Can't remember the time, but it's on Saturdays. David Dunn and I know each other from the HAPS days, and maybe even from the Periscope days. I think the HAPS days. So do follow David Dunn over on Twitch as well if you want more astro space stuff in your life, because of course you do. So we know there is this inherent randomness in quantum physics. And from there, you can see it's a very logical next step to think of, okay, if there is this randomness, can we have every possible outcome each happening in a different universe? And this is what gives rise to this idea that every time you make a decision, there's a different universe. But this is something that we can't really test in any way. It is one of the interpretations of quantum physics, but it's not something that we can really meaningfully discuss beyond that. Now, another idea of the multiverse, and I think this is the one that personally I find a lot more interesting and a lot easier to discuss in terms of the starting points, is the idea that in the early universe there was inflation. Hypothetical, we haven't confirmed this yet, but it's the most likely model we have to explain some things in the universe. So in this idea of inflation, in the early universe, the universe goes from being very, very, very small, still infinitely big but small, to being a lot bigger and a lot colder. It just did this growth. Now, we don't really understand much about inflation because it would be, a fraction of a second, early universe. We don't know. We have a lot of ideas of what couldn't have happened, because else the CMB, the cosmic microwave background radiation, would look different. But we're not completely sure what inflation looked like. And also there's a fun thing that inflation would be so dramatic if it did happen that it would delete the memory of anything that came before. This leads to the idea that you could have pockets of the universe where inflation happens differently or lasts a different amount of time. Maybe here inflation lasted billions of years, maybe here it lasted a second. And inflation sets the kind of initial conditions for what comes next. It sets the starting point for our hot Big Bang cosmology, which tells us about the last 14 billion years of evolution. So in this idea where you could have different amounts of inflation, what you could end up with is different universes or different multiverses that we call them, where the laws of physics are slightly different. Some of them you would have a different electron mass, some would be very similar to ours. Some you would never be able to form life, you would never be able to form structures. Maybe in some you didn't have an imbalance between matter and antimatter in the early universe, so everything is just radiation. So just to put context on that, in our universe, the one we live in, the only one we have access to, in the very early universe, there was matter and there was antimatter, but there was a slightly more amount of matter than antimatter, which is good, because every antimatter particle found a matter particle and annihilated. The antimatter matter come together, radiation. So if every antimatter particle found a corresponding matter particle and annihilated, the only thing that was left was this slight extra matter that we have in the early universe. But we don't know why we had a bit of extra matter. But if we didn't, we wouldn't be here having this conversation. If there had been equal amounts of antimatter and matter, it all would have gone away. But what actually happened is you had something like this. So all of these went away and you were left with a bit of matter left over in our universe. Maybe, depending on how inflation worked, depending on this multiverse, in other multiverses, in other versions of the universe, you could have no imbalance, you could have only antimatter. So this leads to the idea that there could be billions of different universes with different laws of physics. Now and I've heard some people, some experts on inflation, people who have spent their whole career working on inflation and pioneers in the field, make comments like you can't have inflation without multiverse. Now, personally, I don't necessarily believe that. I think we don't know enough about inflation to make that claim. However, whatever version of the multiverse you want to think about, whether it's the one with quantum realities because of the randomness of things, or if it's just this idea where we have universes with different laws of physics, whichever version of the multiverse you want to take, we will never be able to travel to another multiverse. I see there's a comment here by JK saying like maybe there's a multiverse where you're winning the lottery, and maybe if you believe in this idea of different universes with different versions of yourself, unfortunately you will never be able to contact that version of you because we are limited to the information contained within our universe. By definition, our universe is everything we will ever be able to access and everything we have information of and access to. So if there are other multiverses, however they were created, they're completely separate from ours. And there's also the idea that if you could in any way communicate or exchange information, what could happen is that you collapse these two universes. Because let's imagine that here a field is in a specific energy state, like the Higgs field, the one that gives everything mass. It's at a specific energy level. But the universe is lazy. It likes being in the lowest possible energy state. You know, if I balance a pen on its tip, it's going to fall because it's much more energetic for it to be fallen unless I manage to balance it perfectly. But even then, it's going to be metastable because as soon as you knock it, it's going to fall quite dramatically. So, you know, the universe likes being in its lowest energy state, which in the case of this pen is lying down. In the case of humans, it's often lying down as well. So the universe likes being in its lowest energy state. So imagine the Higgs field here, it has some value, and in one of these other multiverses, it had a lower value. If we were able in any way to exchange information with this other multiverse, with this other universe, then the Higgs field here will kind of learn about the lower energy value. This would transfer over, this would move from one universe to the other and drag our universe down to that lower energy state, therefore ending existence in this universe. So this is not like an end of the universe scenario that we expect to happen, not via communicating to another universe. But there is this idea that, you know, if you have any other multiverse, any other version of the universe, how would we ever know this? How would we ever communicate or exchange information? Because by definition, we are limited to our universe. So I think the multiverse is something that is really cool and it gives a lot of ideas to play with. And you know, you can do a lot with it in sci-fi. It's why it's so common in sci-fi. You know, Doctor Strange and the across the multiverse or whatever it's called, the multiverse of madness. We have the Spider-Verse. You have everything all at once all the time. Can't remember exactly what it's called, but you know what I'm talking about. There are so many different versions just in the last few years, and you can go back. There's billions of these examples. Because the multiverse is such a rich thing to play with, it's a favorite trope for sci-fi, and I get it, and I see why. So the question was, any update on multiverse theory? We still have a lot of models. We have a lot of ways where hypothetically we could end up in a multiverse scenario, but we will not be able to jump from one universe to the other. We will probably, even if these other universes do exist, we will probably never be able to access them or exchange energy or exchange information with them. So even if you win the lottery in one of your other multiverses or another version of you wins the lottery, unfortunately, you're not going to be able to do a big party in your new mansion here because you're not going to be able to get that money from the other universe. Not to our knowledge. You know, I'll be happy to be proven wrong on this, unless, of course, that then leads to like, hey, we found a multiverse and now we've destroyed our own universe in the process. Whoops. So I think multiverse is one of those things that's really cool theoretically to discuss, and it's cool to do the maths and to work it out and to talk about the implications and to throw it in sci-fi. But it's not something that I think we're going to really encounter during our lifetime or any of future human. I don't think at any point we're going to be like, here's our look, baby universe, here's one I made at home. You know, like the cooking shows where suddenly they go away like, here's one I made earlier. So then it would be like, here's one I made earlier. So string theory can never be tested. Yeah, string theory is fun. So there's just a slight parallel here, a slight change of direction. String theory is a really cool idea. It's something that, so we've gradually been breaking things into smaller and smaller parts. At some point we thought the atom was the smallest we could go. We called it literally the indivisible. Atom means indivisible. And then we found that atoms are actually made of the nuclei and the atoms. And then we figured out that nuclei are made of protons and neutrons. And then we figured out that protons and neutrons are made of quarks. So you can gradually go lower and lower. And then what are quarks made of? Well, we call them elementary particles. We say that's the lowest we can go. But what if you could break it smaller? So string theory is the idea that everything is basically these kind of strings that vibrate, and the vibration of these strings gives rise to all of the properties that we see. So if a string vibrates one way, it will be a specific quark. If it vibrates a different way, it will be a different type of quark. And this is all very, very, very cool. And it's something that mathematically is extremely elegant. And string theory does offer kind of a way to unite the quantum world and gravity. So gravity is describing how things work on large scales, like why pen falls, why we dramatically to the floor this time, why we stay in orbit around the sun, why the moon stays in orbit around us. This is gravity. Quantum theory, however, is about particles and why particles behave the way they do. And trying to put these together is very difficult because they're very different scales. And trying to match gravity and quantum is very difficult. String theory is a realization of quantum gravity. It gives us a way to put things together. However, string theory requires 11 dimensions. Most versions of string theory require more than 4 or 5 dimensions. The most common one to think of, M theory, requires 11 dimensions. Our universe has 4 to our knowledge. So that means that an 11-dimensional universe is not really a description of our universe. So I think string theory is mathematically really, really cool. And it's something that is really fun to play about with. And you can use a lot of the techniques developed for string theory for other things. The maths is similar. But unfortunately, string theory doesn't seem to apply to the universe we live in because we just have the wrong number of dimensions. And I'm guessing the way we got from multiverse to string theory is through this multiple dimension thing. And I just want to make a comment that multiple dimensions and multiple universes are not necessarily the same thing. So I was just saying that we could have these other versions of the universe where you have different properties or where you have a different outcome of an experiment. Whereas when we're talking about dimensions, what we mean is kind of the things we need to explain a system. So when I say our universe has 4 dimensions, if you want to describe any event in the universe, you need 3 space coordinates and 1 time coordinate. So the space ones, we have up, down, left, right, in, out. These are 3. And then we have time, which only moves forward. If I give you the space, but I don't give you the time, you don't know when an event is happening. And in order to fully describe an event, you just need these 4 coordinates. Multiple dimensions, extra dimensions is this idea that maybe there could be more of these dimensions, of these space and time dimensions that we don't have access to. So it's not completely the same as the multiverse, it's multiple dimensions. But this is something that then in sci-fi is often used interchangeably because people say, like, I'm just jumping to another dimension, when they mean I'm jumping to another multiverse or another version of the universe. So then these things get mixed up often. So if you think dimensions and other versions of the universe are the same thing, don't worry, that's a very common thing because of the way it's portrayed in a lot of sci-fi. But string theory is really this idea that you have extra dimensions, so extra ways of describing how things work. And unfortunately, string theory doesn't really seem to be applicable to our universe, but I'm sure some string theorists would disagree with me on that point. So multiverse, status of multiverse, it's very cool, but we haven't found a multiverse yet, and personally, I don't think we ever will. Likewise, we're limited to 4 dimensions so far. Maybe someday we'll find other ones rolled up in special ways. It doesn't seem to be the case so far. Fun fact, you can also use these like extra dimensions to try to explain dark matter, but it doesn't seem to work, but it's cool. There's also, going back to the CMB, kind of, if you look right where my image ends, so like right here, just to the left of where my finger is, like right there. Just imagine I'm pointing like right here. There's a really dark blue spot. That is what we call the cold spot. It's a region of the cosmic microwave background radiation that is just a bit colder than the other ones. It's kind of a statistical anomaly in that, on average, that region is a hint colder than the rest. And there were a lot of ideas as to what this could be. And at some point, one idea was that this could be kind of a parallel universe or another version of the universe, one of these multiverses that is like brushing up against stars, not really close enough to have any noticeable difference, except to slightly cool down the CMB photons. Unfortunately, or fortunately, depending on your perspective, that doesn't seem to work with the latest CMB data. With the latest data of the cosmic microwave background radiation, this cold spot it's a bit still unclear what it is. So the blue area at the center looks very blue, very cold. I agree, it does. But you have to think that this here is kind of a map of the whole sky, so the edges are slightly squashed together. So the part in the middle is very cold but spread over a larger region. I realize I just got rid of myself here. So this region right down here doesn't look any bluer than other regions, but it's a tiny spot that is very concentrated. And it's the fact that, especially because it's here at the edge, it's actually a bit bigger than what it looks like here. So it's this tiny spot down here. You might think, okay, but up there's also blue spots. Over that way, there's also blue spots. But there's this region here. Would be very nice if I could actually draw on my slides, but I can't do that yet. But the region's just like right here, if you imagine right where my finger is. This one is just statistically a bit colder than the others, and this is something that you can't really see by eye, because by eye you're very right, James, that in the center looks equally cold, but it's really the anomaly part is this part down here, the weird part. So when you talk about extra dimensions, when you talk about multiverse, there's a lot of different things you can throw about, especially when you're talking about extra dimensions. You could get to string theory, you get to dark matter, you get to random stuff like this. When we talk about the multiverse, of course, we get to talk about inflation. We get to talk about quantum physics. So they're really, really, really cool topics. I don't work on multiverse. I don't work on string theory. I don't work on these cool topics, but it's very fun to think about. It would be cool if someone would make a website or app with a globe-shaped spinnable CMB. It would be. There was a conference, I think it's about 20, 25 years ago, that was all about Planck. Back in the days before I joined the field, there was a Planck conference. And, anytime you go to a conference, you get conference gifts. And that's really, really cool. Like, sometimes they give you mugs. I have conference mugs, which I love. I have a travel mug from a conference from 6 years ago, and it's my favorite mug. It's an amazing travel mug. Sometimes you get random shit like a pen, or this notepad that I'm using here. This is from a conference I went to. So is the pen, actually. These two were a match. But I digress, as always. At this Planck conference, there were inflatable volleyballs, like beach volleyballs, with the CMB printed on it. So you could actually get like a ball with the CMB printed on it, and I want one. Fun fact, there is one currently hanging in the office building. It belongs to one of the professors who was at that Planck conference, but it's just hanging in the hallway. Second fun fact, if you ever see that ball in my house, I absolutely did not steal it. But yes, I have told people that someday I'm going to steal that ball. So yeah, you could actually get like this volleyball with the CMB on it, and that is amazing, and I need that. As to having an app where you can have the CMB, we actually thought about this. So this is something I don't promote as much as I should, but I was involved in a Cosmology game. It's available at the App Store and on the Play Store, Apple Play, the App Store. Wherever you normally get your apps, Google Play, the App Store, those are the two. There's a game called Dark Master that I was involved in. I was kind of the scientific advisor on this game. And it's a game where you play as different particles and you travel throughout the history of the universe. And your mission changes depending on what particles you are. It's got very simple gameplay and it's extremely addictive. And I encourage you all to download it. The game is called Dark Master. Available in all of the usual places. Please do download it. I don't get any money or commission from it. I just think, we put a lot of work into it. And you get, every time you fail at a level, you get a pop-up giving you cosmology facts, and I wrote all of those. So, please do check it out. But the reason I mention this is because when we had this master student working on the game, and when we were brainstorming ideas of what's going to happen, one idea we came up with was similar to Stellarium, or the typical stars charts where you pointed at a part of the sky and you get the stars and you can see what's there. We actually thought about doing that with the CMB. So like wrapping the CMB as a background in one of these apps so that when you pointed your phone somewhere, you could peel away every level. And kind of like first you'd see the stars and then the galaxies and go back and go back. And the last thing, like if you zoom in enough, you'd end up with the CMB. And then we'd highlight different spots. Like this is the spot that Planck first measured. This is the spot that this. And that was one of our ideas. And in the end, we went for the Dark Master idea, which I think is much better gameplay. But I agree with you, Paul. I know I'm digressing here, but I agree with you, Paul, that it would be really cool for someone to actually either make this app where you can point and see different parts of the CMB, or just where you could like play about with it. I think it would be really, really cool. Also, someone should like laser etch it into glass, so like it's a tactile version. That would be amazing, with like bumps and dips corresponding to the temperature. And then you'd even have a like one that doesn't require seeing, that you could just feel it. It would be tactile. That would be amazing. Someone please make this. I will absolutely back it on Kickstarter, on whatever. Please make this happen. Like, I know, like 5 minutes into the stream, there was a question about magnetars. I have not forgotten magnetars. It is gonna be answered, but now we're on the CMB and dark matter and stuff, so we're gonna stick to this. We will, the multiverse question threw us off on a lot of tangents, but I will get back to magnetars in a minute. Let me just check that I answered all the questions that were coming in here. I talked about the blue and the hotspots. We talked about multiverse. Then there was this comment from Ben. What is the cosmic neutrino background, and is it the same thing as microwave background? Okay, actually, let's pin that one. Let's answer magnetars first, and then come back to cosmic neutrino background, because cosmic neutrino background is amazing. But there was this comment about magnetars quite early in, so let's go to that one, because I was asking for questions, and JK asked something about magnetars, so I should answer that. So the question at 8 minutes past, so quite a while ago by now, 35 minutes. Thank you for bearing with me here. Just read about magnetars. Neutron stars just got cooler. Are magnetars part of your current research with neutron stars and gravitational waves? Excellent question. So a magnetar is a rapidly rotating neutron star. A neutron star is a star that is so dense that protons and electrons are pushed together to form neutrons. So you end up with a star made entirely of neutrons, which also means it's extremely dense. Made it 40 minutes without a coughing fit, and now my lungs are like, yeah, I don't like this anymore. Okay, so magnetar, rapidly rotating neutron star. Neutron star is a star that is so dense that protons and electrons are pushed together to form neutrons. So you have a really, really dense star. This really dense star can have really active magnetic fields. When it starts rotating, you end up with really rapidly rotating magnetic fields around it. This is really cool. This is something that is very difficult to study because you have weird property, like weird type of matter where it's just neutron matter is weird. Then you have the whole magnetic fields making everything really confusing and really funky. And if you get neutron stars close enough together, they're going to start spiraling and smashing together, and this is going to produce gravitational waves, which is very, very fun. Now, neutron stars, and so I work on gravitational waves produced in the very, very early universe. So what I work on right now is asking the question, JK, is your multiverse you? Okay, logged into wrong account. Okay, good to know that you're the same person. I was wondering, like, who's JK? Haven't met that person. Welcome. Nice to have you here now, James, as well. Okay, so James asked the magnetar question. So yeah, what I work on currently is very early universe gravitational waves. So basically asking the question of when the early universe finished inflation, after inflation, when everything was really high energy and the forces broke away, could there have been something at the time that produced gravitational waves? And if so, can we ever see these gravitational waves with missions like LISA in the future? And then follow up, can we connect this to dark matter? That's what I work on. Now, I don't work on neutron stars directly. Neutron stars can produce gravitational waves when merging, but the place where there's a big connection between studying neutron stars and what I do is when you study this thing I mentioned in the early universe where the forces break away. This would trigger what we call a phase transition, similar to when you boil water and it goes from liquid to solid. You can trigger a phase transition in the early universe. Depending how this phase transition happens, you can produce gravitational waves. So in order to get the gravitational waves that I want to see, we assume certain things about this phase transition. Now, when you have a neutron star, inside the neutron star, when you're pushing protons and electrons together, the matter behaves in a way that is also basically a phase transition. You're transitioning from one state to this like really high dense neutron matter. And it turns out that the way you describe the phase transitions in the neutron star and the way we describe these early universe phase transitions is very similar. So there are people in my building, in my research group, in the broader research group, working on neutron stars. And the language we use to describe them is very similar, which is very cool because then when we're talking to each other, you can see that there's like a common ground there. I'm actually planning, I'm trying to get someone from the neutron star group to come on Cup of Cosmology and tell you all about why we study neutron stars in a group that also does gravitational waves. So, short answer to that question, magnetars are extremely cool. Neutrons can produce neutron stars can produce gravitational waves when they smash together. These are not the same type of gravitational waves that I'm looking for in the early universe, but the physics that we use to describe these early universe gravitational waves, or the production of these early universe gravitational waves, is similar to the physics we use to describe neutron stars. So there is a connection, but not directly. But magnetars are very, very cool. I left my tea a bit too long today, and now it's getting cold. And I'm speaking very quickly, so tea is giving me a good way to catch my breath and drink tea. Everyone needs more tea. Tea is good for your soul and good for your throat as well if you have a lingering cough. Okay, question from Ben. I hope that magnetar comment answers your question, James. So, question from Ben, which I really like. What is the cosmic neutrino background, and is it the same thing as the microwave background? Love this question. So when we talk about the particles that make up the universe, the normal matter of the universe, let's not talk about dark matter and dark energy, but the normal matter of the universe, when we talk about the particles that make these things up, we have the quarks, which are the ones that can be found alone. They need to be bound together. That's where you have up, down, top, bottom, strange, and charm. Then those are the quarks. Then you have the fermions, quarks and leptons. Yes, sorry, the leptons. Then you have the leptons. The leptons are also fermions, so they're not bosons. The bosons are the ones that tell the other particles how to interact. The fermions are made up of the quarks and the leptons, and the leptons are ones that can be found free, but they also make stuff up. So inside this family, you have the electrons and you have the neutrinos. Then you have the bosons, which are the ones that tell the other particles how they can talk to each other, and there you have photons, particles of light, gluons, W and Z bosons, and the Higgs boson. We don't know what that's doing, but that's there, and gravity, who knows. But neutrinos. Let's talk about neutrinos. Neutrinos are these tiny, tiny, tiny particles that for many years we thought were massless, but are actually not massless, and they're particles that travel almost at the speed of light. They're zipping through the universe, but not quite the speed of light because they have mass. And neutrinos do a very fun thing. There are 3 types of neutrinos: electron neutrino, muon neutrino, and tau neutrino. And a neutrino can change which one it is. So a neutrino can be created in the sun as an electron neutrino, and by the time it reaches Earth, it can be a muon neutrino or a tau neutrino. And the fact that they change flavor means that they also must have mass in order to do this change, because there's kind of a connection between the flavor and the mass, not directly. Like you can't say an electron neutrino has this mass, but the fact that you can change means they have mass, which also means they don't travel at the speed of light, which is very fun. Just imagine if you go to the shop and you buy vanilla ice cream, and by the time you get home, it's strawberry ice cream, and then you put it in the freezer, you open it the next day, and it's chocolate ice cream. This is what neutrinos do. They change their flavor. And this is very, very cool. Now, neutrinos are extremely difficult to detect because neutrinos do not interact via the electromagnetic force. So they have mass, they interact via the weak force, but they do not interact via the electromagnetic force, which means they are invisible. The only way neutrinos talk to other particles is via the weak force, which is very weak and hard to measure. And now some of you might be thinking, wait, a particle that has mass and that doesn't interact electromagnetically, this is starting to sound a lot like dark matter, and you're not wrong, and you're not the only one to think this. So there is the question of, can neutrinos be dark matter? Short answer is no. At least not all of it, because neutrinos travel really quickly in the universe. They're quite light, they travel really quickly. And we know that dark matter needs to be a bit slower If not, we wouldn't have galaxies. So if all of the dark matter were in the form of neutrinos, we wouldn't have galaxies because it would wash them out. You wouldn't be able to form these big structures. So the fact that we have galaxies and that we see these structures means that we can't have all of the dark matter in the form of neutrinos. Also, we know how many neutrinos there are in the universe. We can take their overall energy, and it would only contribute a fraction of a percent of the dark matter. So even if you say neutrinos it should be a part of dark matter, they cannot be all of the dark matter, at most a sub-percent. Okay, so neutrinos interact via the weak force. Why does this matter? Because in the early universe, the weak force was more important. Then, as the universe cooled down, these different things broke away. So when I talked about the cosmic microwave background radiation earlier, this map here, I mentioned that we had protons, electrons, and photons. The electrons and the protons bind together to form hydrogen, and the photons break away. This is what we call a decoupling. The photons decoupled, so the particles of light decoupled from everything else. This happened when the electromagnetic force, so when specific interactions became more favorable. So when the protons and the electrons could combine together, when you can do this kind of interaction, then you stop bumping, the photons stop bumping into the electrons and break away, they decouple. But a lot of other particles can have this decoupling. For an example, neutrinos. So if neutrinos only interact via the weak force, which is what we suspect they do, it means they, at some point in the very, very early universe, they were talking to the rest of the particles via the weak force. As the universe cooled down and this weak force became less important and the electromagnetic force became more important, the neutrinos broke away. So neutrinos had their own decoupling. This means that the neutrinos that broke away in the very early universe, like a minute after the end of inflation, these neutrinos have been traveling freely ever since. And today, they would make up a cosmic neutrino background. So behind the cosmic microwave background, behind that, there could be a background, or we predict there to be a background of neutrinos. These are neutrinos that broke away in the first few minutes of the universe and have been traveling freely ever since, getting cooler and cooler. These are ridiculously difficult to measure. So there are billions of neutrinos in the universe. Like if I hold up my thumb, every second, 60 billion neutrinos go through the tip of my thumb. 60 billion. We don't feel them because they do not interact. They're just doing their own thing. But if we could ever measure these neutrinos that are behind everything, that are zipping through us, it would. So in the same way that this shows us what the universe looked like 380,000 years after the end of inflation. Imagine if we could get something similar for neutrinos. It would show us what the universe looked like 3 minutes after the end of inflation. So the cosmic neutrino background is a prediction. We expect it to be there. It would be really, really, really cool if we could ever measure it, but it is going to be extremely difficult to measure because it is behind everything else. It is really hard to get the sensitivity you need to be able to measure this. We are good at measuring high energy neutrinos, but these neutrinos in the cosmic neutrino background would be low energy. They spent billions of years traveling and cooling down and getting cooler and harder to detect. But it is going to be there. We expect it's going to be there. We just need to find it someday. And I'm not sure, I'm just gonna, no, I just remembered I don't have the slide. So one of the reasons this is important is because when we look for dark matter, we're also looking for something that at some point broke away, that used to be interacting via the weak force, because we think dark matter talk to the standard model via the weak force. So we're looking for something that used to be talking to the standard models and to normal particles and broke away, which means we're looking for something that is similar to neutrinos but more massive. So anytime we look for dark matter, there's a plot we draw of like the exclusion bound, and on one side there is how much they talk to the standard model particles, and on the other side there is the mass. And all of the experiments we have to directly find dark matter is trying to reconstruct these early universe conditions where with the weak interactions you could see dark matter interacting via the weak interactions with normal particles. And at the bottom of this plot, there's always what we call the neutrino floor. And if we can push our detectors to reach that sensitivity, we would not be able to tell apart neutrinos from dark matter. So we would not be able to measure dark matter at that point. And there's a fun thing that in dark matter experiments, we're getting closer and closer and closer to the neutrino floor, but we still haven't found dark matter, which is fun. Which is why people like myself then say, okay, maybe dark matter was never weakly coupled or weakly interacting with the standard model. Point being, there is this neutrino background there at the bottom. And this is something we're hoping to find one day. There are proposed experiments like Ptolemy, so that's Ptolmey, Ptolemy. Ptolemy would be an experiment sent to space away from any other interference that would measure a specific way that neutrinos can decay and try to measure this in the universe to find the cosmic neutrino background. So cosmic neutrino background is amazing. I really hope we'll measure it someday. I just think it's going to be really, really hard. Like the dream, right? The dream would be to have side by side the cosmic microwave background, this map here, next to it, the cosmic neutrino background, a map similar to this one, but of neutrinos. And then a third map of the gravitational wave background produced in the very early universe. Because that would give us the universe 380,000 years after inflation, the universe a few minutes after the end of inflation, and the universe a fraction of a second after the end of inflation. That would be an amazing thing to achieve. I really hope that like 50 years from now, someone is doing this type of science outreach, probably in VR or something like that. I'm like, look, here's the cosmic neutrino background. Look, here's the gravitational wave background. I think these things are far away. We're not going to get them anytime soon, but it would be amazing if we did. So yeah, cosmic neutrino background is the neutrino equivalent of the cosmic microwave background radiation. It's something that is very, very, very cool. It's something that I really hope we will measure someday. And maybe it's sooner than we think. I'm not sure which we will get first, the cosmic neutrino background or the stochastic gravitational wave background, because the difference is we know for sure that the cosmic neutrino background is the same, or we know as sure as we can, we're pretty sure it's there. Whereas the gravitational wave background depends a lot on your models, on your theories, and then there's the problem that there's a lot of astrophysics in the way. A lot of galaxies, a lot of neutron stars smashing together, a lot of white dwarfs smashing together. So not only do we need to first measure some background, then we need to separate the astrophysics from the cosmology. So maybe a cosmic neutrino background measurement would be sooner than a cosmic gravitational wave background. Both would be amazing and would tell us a huge amount of information about the early universe. I think I would be equally excited about both, to be honest. Maybe more so about the gravitational wave one, because that implies new physics. Whereas the cosmic neutrino one is like, yes, we predicted this, look, we found it, which is also very cool. So I know nobody asked about the gravitational wave one, but those are like the three maps we want. CMB, we've done that, that's good. Now we can move on to the neutrino one and the gravitational wave one. Of course, there's a lot more you can do with all of these. But it would be very cool to have these three maps one day. So those were some very fun questions today. I feel like there weren't too many questions, but we got to go really in detail with some. So we talked about dark matter, dark energy, the CMB early on in the stream. Then I went through the multiverse and inflation and string theory, which is always fun. Some digressions into dark matter along the way. Then we talked about magnetars and a very fun conversation about the cosmic neutrino background. I love all of these topics. They're really fun. See, this is something I love about these streams. Every time I log on, I don't know what you're going to ask me. It's really fun because I come on like, let's see what I'm going to get to talk about today. Science is amazing. I have random facts about random things in my brain and I get to share them with you. It's like I get to info dump about something I love for an hour. It's great. And every week I come in like, what are they going to ask me today? And it's great when you ask me random things or stuff that doesn't come up often. Like we don't often talk about the multiverse or string theory. We always talk about dark matter. But it's great to have these different topics. So thank you everyone for all your questions. It's really nice to have you come here. While going through and cleaning up my Twitter account, which I was doing today again, I keep doing this, it's a slow process. I was finding some tweets from like 8 years ago. And there were some of you who are still in the room here 8 years ago making comments like, hey, great stream. And you're still here. I still find this amazing that you've all stuck with me so long. So thank you. Those of you who have been around for 8 years, those of you who are here your second week or your first week, thank you. Really, the reason I do Cup of Cosmology is because of people like you coming in every week asking me questions. It's so fun, and I really like doing Cup of Cosmology. And I love that you all come in and ask me questions and chat to me and chat amongst yourselves. It's really, really fun. So Cup of Cosmology will be back online next Sunday, same time as today. That is 10 a. I'm doing times backwards. That is 7 p.m. Central European Time, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. Save your old Twitter feed for the future Cup of Cosmology Museum. Unfortunately, my old Twitter feed has already gone, but all of my Periscope streams, with the exception of about 10% of them, so about 90% of my Periscope streams, I have backed up on a hard drive. Like, I downloaded them. At some point, I will upload them all to YouTube. I also have all of my HAP streams. Every single HAP stream is downloaded and backed up. At some point, I will gradually upload those to YouTube as well. And all of the streams I've done since January 22, January 22, are on YouTube. So almost all of my streams are backed up somewhere. We don't need the Twitter feed for that. All of the streams are backed up. Eventually, there will be like the Cup of Cosmology collection. And you can all go back and watch my first stream where they're like, oh my God, what do I do? How do I talk to people? We've come a long way since then, hopefully. So the Twitter feed is going, but the streams live on a hard drive somewhere. I should probably back that up because they're literally only on one hard drive. So that's a nice reminder for me to back that up. So anyway, as you know, I'm no longer on Twitter. You can find me on Mastodon, DC Hooper 91_Cosmo on astrodon.social, or for my more personal ramblings, DC Hooper 91 at tech.lgbt. That one's a bit random. And of course, for Cup of Cosmology, you should make sure you follow the YouTube channel. You can also follow me over on Twitch. One nice thing about Twitch is that there's a scheduler, so you can already see on Twitch when I'm next going live. For now, it's just set every Sunday, and I'll cancel events if they're not happening. Wherever you're following, make sure you follow, subscribe, leave comment, ring the bell, all of the usual stuff. It really, really does help a lot more than I think you all realize. So thank you for doing all of that. As I said, it's been great to chat to you all today. I've really loved the questions. I hope you'll all tune in next week. Cup of Cosmology will be back online next Sunday, same time as usual. I hope to see you all again then, and I hope in the meantime you all stay safe and take care of each other.